The allocation of memory is broadly done in two partitions. One partition is for the operating system and the other partition is for the user processes. Now the OS can be placed in either the low memory addresses or on the high memory addresses. Here we are assuming that the operating system is available in the higher memory addresses. So what do we understand by the contiguous memory allocation technique? In this, each process is contained in a single section of the memory. So suppose we have process 1, so it will be contained in one single section of the memory. And this section would be contiguous to the section which is containing the next process. So there would be contiguous memory allocation to each of these processes and each would be available in a single section of the memory. Now there is a base register which will be keeping the smallest address from where that process is starting, and there would be a maximum address which a particular process can access. So this would be specified by the limit of this particular process. So the base plus limit would be referring to the highest memory address that a particular process can access. No process is allowed to access the address space of another process. So that means any address which a process accesses will have to be less than the base plus limit of that particular process. So in case of process 1, this is the base address which has been allocated to this, and this is the base plus limit. So any address which this process accesses is valid only if it lies within this range. Similarly, each process will have its own base and a maximum address which it can access. So to protect the user processes from accessing the space of each other, relocation registers are used. We know that the base register contains the value of the smallest physical address. So this is the base register which will be containing the value of the smallest physical address. The limit register contains the range of logical addresses. So this is the limit register which will be containing the maximum that a particular process can access. So any address that is generated by the CPU which is belonging to a particular process, that means it must be less than the value contained in the limit register. So let's say this is the CPU which is generating the logical address, and this logical address has to be less than the value in the limit register. So this comparison is done in the MMU, and if it is less than this, then it is allowed to pass through, otherwise an error condition will be raised and a trap will be sent to the system. Now if the value of the logical address is less than the value in the limit register, then it will be added to the value in the relocation register. So relocation register specifies where exactly in the memory, in the actual physical memory, the process has to be placed. So let's say the value in the relocation address register is 2000. That means this particular logical address has to be added with 2000 to go to that particular address. This means that 2000 is the base address of that particular process. So this is the base which is stored in the relocation register. This will be added to the logical address of the process, and now this particular memory address can be accessed. So in this way, the system ensures that no process accesses the address space of any other process. It will always be within the range that has been specified for that process. And the memory management unit will take care of this and will map the logical address dynamically to the physical address. Now, in this contiguous memory allocation, each partition or each section is not of the same size. It can be of variable partition sizes. So, now if the different partitions are available, different partition sizes are available, then the operating system will have to keep the information of the parts of the memory which are available and which are occupied. Initially, all memory is available for user processes. So let's say this was the status of the RAM after a few processes have been brought into the memory. So initially we just had OS and all of this user space was available for bringing the processes. Now these processes have been brought in the memory. Now if let's say process 8 completes and leaves the memory, then this block of memory which is now available is referred to as a hole. So this is a hole, that means it is a block of available memory. That means if a new process has to be brought into the memory, then it can be brought and placed into this hole as long as the requirement of that process is less than the size of this hole. So there is a possibility that holes of various sizes may be scattered throughout the memory. Let's say after this state of the memory, process 9 was brought in. So it was brought into a part of the hole and now only this part of the hole is left. So this is only the available memory that is available now. If process 5 leaves now, so then we will see that again another hole is being created. So this way, as the processes come and leave the memory, holes may be created and they may be scattered throughout the memory. So whenever a process arrives, we allocate memory from that hole which is large enough to accommodate it. So let's say this is of 50 MB, 50 megabytes memory, let's say, and this is 30 megabytes. So if a process which is coming in requires 40 megabytes of memory, then it can be placed in this particular hole because this hole is larger than the requirement of the process. And when the process exits, it frees this partition or the section of the memory that was allocated to it. And if the partitions, the free partitions are adjacent to each other, then they can be combined. So let's talk about dynamic storage allocation problem using the variable partition sizes. So if there is a list of free holes and there is a request of a process which requires n size of memory, then how do we take care of this allocation? What are the algorithms that can be followed to allocate n size from a list of free holes? So one of the algorithms is the first fit algorithm. That means allocate the first hole that is big enough. So if you look at the memory at this point, we are not assuming that the operating system is also over here in part of the memory. So this is the user space that we are showing over here, and we have only process 3 and process 5 in the memory currently, and there are a few holes. So this is, let's call it hole 1 of size 30 MB. This is hole 2 and this is hole 3 of size 50 MB. Now there is a process which comes and it requires, let's say, 40 megabytes of memory. Now the operating system has information about all the available memory. So what it can do if it follows the first fit algorithm is to find that first hole that is big enough. So it checks the details of hole 1, it is 30 MB. It is not large enough to fit the requirement of 40 MB. So it checks the next hole, yes. Now 70 MB is larger than 40 MB. That means this new process which is coming in can be placed over here. 40 MB will be utilized and now only a 30 MB hole will be left. So this information will now be updated. So instead of this being 70 megabytes, now we will be updating it to the 30 MB information. So in the first fit algorithm, the operating system will check what is the first hole that is big enough to satisfy the request of the coming process so that it can be allocated, and the information about that hole will be updated. The next algorithm is the best fit algorithm. In the best fit algorithm, the smallest hole which is big enough to accommodate this request will be used to put in this process. So what does this mean? So we have a hole of 30 MB, we have a hole of 70 MB and a hole of 50 MB. So the first fit would have put the process in this hole, but in the best fit, this whole list will be checked, and that hole which is just big enough to handle this particular requirement will be taken. So we can see that 50 MB, this hole is just big enough and it is the smallest hole. So we have two candidates over here, one is 70 and one is 50, but we can see that 50 is just big enough to be granted to this process. So 40 MB will be used by this process, and now the whole information will be that only a 10 MB hole is available. The drawback is that the entire list has to be searched. The way of handling it is that the list can be ordered by size. So whichever is the first hole which is coming, which is just large enough from this requirement, can be considered. The advantage of using this algorithm is that it produces the smallest leftover hole. So we can see that in this hole, when it was given to the process, the leftover hole is only of 10 MB. Had this 40 MB come in this particular hole, then it would have left a hole of only 30 MB. Now 30 MB, that means would have been used for some other process. In this case, we can use the complete 70 MB for a new process, and this leaves a very small hole of 10 MB. So the best fit algorithm works in this manner. The third algorithm is the worst fit algorithm. Here it will allocate the largest hole. So if the request is for 40 MB and the holes are of size 30, 70 and 50, candidate holes are this and this. So out of these two, it will handle the largest hole to this particular request. That means 70 MB will be allocated to the process, and this will result in a 30 MB hole, and now this is available. It still remains the same as 50 MB. The intuition behind it is that it produces the largest leftover hole. Rather than having the small holes which are available in the memory sections, if we use the best fit, this will produce the largest leftover hole. Again, the disadvantage is that again the entire list has to be searched. It has been seen empirically that first fit and the best fit are better than the worst fit in terms of speed and storage utilization. Now let's see a look at a problem which is fragmentation, which is associated with this kind of contiguous memory allocation. First, let us take a look at external fragmentation. External fragmentation means the holes which are created in the whole of memory and which are scattered throughout the memory. So let's say this was 30 MB, this was 50 MB hole, and this is a 40 MB hole. So the total over here right now, if we see, is 120 MB in holes. But let's say that a requirement for a process comes which is of 100 MB size. So a process comes which requires 100 MB. So even though the total available space in the memory is 120 MB, it is unable to fulfill this new request of 100 MB which has come in, because these holes are scattered all over the memory. So there exists total memory space to satisfy a request, but it is not contiguous, it is scattered. So this is referred to as external fragmentation. The memory has been fragmented or broken down. So there is memory which is available, but it has been broken down into parts. So contiguous memory is not available, and because we are dealing with contiguous memory allocation, that means this request of a particular process cannot be granted. Now there is another concept which is referred to as the internal fragmentation. This refers to the difference in the memory internal to a partition. This happens when the allocated memory is slightly larger than the requested memory. Let's say a process requires 28 MB of memory. Let's say this is the requirement of a process, and now this particular section has been allocated to the request. So if 30 MB, which is slightly larger than the request, is allocated, so there would be at least some part of the memory over here which will be unused. So this difference in the memory which is internal to a partition but not being used is referred to as the internal fragmentation, and this happens when the allocated memory is slightly larger than the requested memory. So this part is being used by the process, for 28 MB is being used, but this 2 MB is leading to the internal fragmentation. Now it has been seen that the first fit algorithm states that if n blocks have been allocated, like in this case, this block has been allocated to a process and this block has been allocated to a process. So if n blocks are allocated, this refers to the size, then 0.5 n blocks are lost to fragmentation. That means 1/3 of the size of the allocated blocks is unusable, and this is referred to as the 50% rule. So how can we take care of this problem of fragmentation? This can be done by using a method which is called compaction. Here all the memory contents are shuffled so that all the free memory is placed together in one large block. That means this block will be moved up and this block will be moved up, this process will be moved down. So all these free blocks are now put together, and this is referred to as compaction. Now this compaction is possible only if the logical to physical address mapping is done at execution time. If that mapping has been done at compile time or load time, then the physical address is fixed, and then this compaction and shuffling of memory cannot be done. But if dynamically it is being allocated at execution time, then this compaction is possible. So this compaction will reduce fragmentation because it will merge all the holes together and form one large hole. So at the end of compaction, we will have one large hole, and so all the processes will come on one side and all the holes will come on the other side, and this will lead to a one large hole which can be used for the requesting processes. So the simplest compaction algorithm is to move all processes towards one end of the memory and all holes move in the other direction. But this is an expensive solution because it requires that after every period of some time, a compaction algorithm must run to move and shuffle all the memory holes on one side. Now another possible solution to this problem is that we allow the address space of the processes to be non-contiguous. That means right now we are giving one contiguous space to the process. We are not allowing it to be broken down into chunks. And now, so if any process comes and let's say there is no hole which is large enough to fit that process, then this hole cannot be allocated because we are using contiguous memory allocation. So if we want to avoid this problem of fragmentation, what we can do is we can use a non-contiguous memory to that process. That means a particular process can be broken down. Let's say the requirement is for 100 MB, then a part of the process can be put somewhere in this part, in this section, another part can be put in another section, and so on. So a non-contiguous memory allocation can also be a solution to the fragmentation. That means the process will be allocated physical memory wherever the memory is available. And this strategy is used in paging, which is the most common memory management technique, and this we will cover in the next video.